A massive question on gravitation. This includes two spherical stars A and B. You read the question and you will find that the two stars have same radius and their masses are related as this. And their densities are different, rho A and rho B. Now what happens is, due to some interaction between the two stars, one of the stars A loses some of its mass, reduces its radius to r by 2. The spherical shape is retained and its density remains rho A. The some mass that is lost by A, that entire mass is deposited as a thick spherical shell on the surface of B, with the density of the shell remaining rho A. Point to be noted, density of the shell. Now VA and VB are the escape velocities of A and B after the interaction process, and its radius of A is half. This is all the question is about. Now about escape velocity, I'll give you a brief, you can say, support on the escape velocity idea. In case if you want a review on that, then this is how it goes. Let's say the velocity at the surface of projection is equal to u, then kinetic energy at the surface minus g mm by r is the potential energy at the surface of the planet. This is the total energy at the surface of the planet. At a height h, when the planet reaches a height h, let its velocity is v. Then half m v square is the kinetic energy at height h, and minus g mm by r plus h is the potential energy at that height. Now what happens is, if I am saying that this kinetic energy has to be non-zero positive, then the velocity has to be positive at height h, then what we can say is half m u square minus g mm by capital R, that is the entire of the left hand side, plus this value of g mm by r plus h should be equal to half mv square. Since this thing is required to be positive, and since this thing is essentially positive when brought to the left hand side, the onus of remaining positive otherwise remains entirely on these two. And that means the critical value of the projection velocity, which is, you can say, should be the escape velocity, should be such that this remains at least 0. And then the half mu square value minus g mm by capital R should be at least 0. And that means these two should be at least equal. And then if the small m gets cancelled, then u square is equal to 2gm by capital R, and root over of that is equal to velocity of escape from the surface of that planet. Now let us enter into this question with elaborate understanding. We will make some schematics to understand the situation of the question and then proceed with it. We will go in a reasonably good speed, but we will not hurry with the situation. I hope you must have noted down the question by now, or else you can go behind on the video and then note the question if you want and get back on the solving from this point onwards. Now, while solving the question, how do we draw the diagram and relate the entities or parameters that has been given is something like this. What they say in the question is the two stars A and B, let's say before interaction, we take a situation before interaction, they have the same radius. So if they have the same radius, let's say their radius remains capital R before interaction. This is star A and this is star B. The densities are rho A and rho B. The masses are MA and MB. Let's say MA is equal to M, then this is equal to 2M. As per the question, densities are given, A and B have the same radii and their masses are related as MB equal to 2 times MA. Now due to an interaction process, star A loses some of its mass and its radius is halved. So that its radius is halved. That means after the interaction, the situation is going to be like this. This is going to be R by 2 for star A, and its density still remains rho A. Whereas on the second star B, this particular original radius of R was for B. Now on top of that, what has happened? A spherical shell has formed, and this spherical shell is belonging to the mass that has been lost by A, and therefore the density of this particular cloud is going to remain rho A, whereas the density here is going to remain rho B. There are two different densities for two different masses over here. Now, let's get back to the question again. Due to an interaction process, star A loses some of its mass so that its radius is halved while its spherical shape is retained and its density remains rho A. The entire mass lost by A is deposited as a thick spherical shell on B with the density of the shell being rho A. The density of the shell remains rho A if the escape velocities have a ratio. Now let us talk on this. To begin with, you see, this is mass and the volume of both is constant. Volume initially for both of them would be 4 by 3 pi r cube. So if density rho A is a rho is equal to m by 4 by 3 pi r cube, by that understanding, this density rho B is going to be twice of the mass by the same volume, that is, this is 2m by 4 by 3 pi r cube, and therefore this is 2 times rho A, or is equal to 2 rho. You can say this is also equal to 2 rho if it is needed. Now, when this particular radius is halved, that means the mass of this star A has been changed. And let's say the new mass for this is m1, and the new mass for this, this mass still remains mb, and mb is equal to 2m. This remains constant. This does not change. This is m and this is 2m. Now this is m1. This has changed, and this particular m1 is equal to how much? Let's see. Now, if this is equal to m1, then m1 by 4 by 3 pi r by 2 whole cube. That means r cube by 8 is going to be the volume. This is mass per unit volume, this is density, and this still remains equal to rho. Now see dear, if this 8 is brought up, that means this is the original volume and this is the new mass compared to the old mass, and then that means if this is the case, 8m1 should be equal to m, and therefore m1 is equal to m by 8. 1/8 the original mass this one is right now carrying, and that means this particular mass which is here is 7m by 8 is in this particular thick shell that is deposited over here. Now this 7m by 8 and this 2m together constitute m2, and that is 2m plus 7m by 8. So that is equal to how much? Let's say 16 plus 7, 23 by 8m. This is the new mass of this entire body. Now, this particular density remains constant. Now, here is the interesting part of the question. Let's say this thickness is equal to some h. Then, the density rho A over here, which is equal to m by 4 by 3 pi r cube as per original calculation. As per original calculation is equal to, as of now, 7m by 8 as the mass, and the volume that it occupies is 4 by 3 pi. Total thickness, that is r plus h whole cube minus r cube as the inner thickness of the shell is h. So r plus h total radius minus r. So this is going to be the calculation. Now, when you compare this with this, what exactly do you get? 4 by 3. Now wait, just a moment. We can therefore write m by 4 by 3 pi r cube is equal to 7 by 8 of m and upon 4 by 3 pi. Let's say r cube is taken out. That means this can become r plus h by r whole cube minus 1. Think on this. You divide by r cube, bring r cube out, and r plus h by r whole cube minus 1. Now when you equate, what you get is m by this particular volume, m by this volume goes off, and therefore 7 by 8 on this side, that is 7 by 8 on the other side, remains. This goes, and this r plus h whole cube by r cube minus 1. This thing comes this side, equates to 7 by 8, and m by this goes off. and therefore r plus h by r whole cube is equal to 7 by 8 plus 1, and that is equal to 15 by 8. When you take a cube root, r plus h by, let's say, capital R is equal to 15 to the power 1 by 3 upon 2. This is a value of r plus h by r after the interaction process. Now what they have asked? What they have asked is the ratio of the escape velocities. Now you see the ratio of the escape velocities are dependent on exactly what things. As we just discussed, V escape is equal to root over of 2 gm by r. 2 gm by r. It is dependent on this. That means mass upon radius ratio plays the game, and therefore if you see that the escape velocities are VA and VB respectively, or VB by VA respectively, then VB by VA will be equal to a root over, of course, 2G is going to get cancelled, and then M1 by M2, no, M2 by M1 into R1 by R2. See, directly proportional to mass, therefore M2 by M1, and inversely proportional to radius, therefore R1 by R2. And now this is R2, this is R1. So therefore I can say that VB by VA calculation is going to be M2 by M1 calculation. Where is your M2? 23 by 8. Where is your M1? M by 8. Now that means you can say M2 by M1 is going to be simply 23. This is going to be a simple 23 into R1 by R2, and that means R1. R1 means this is equal to R1. And what is equal to R2? R2 is going to be equal to R plus H, the radius after interaction, escape velocity after interaction. So R1 is going to be R by 2, and upon R2 is going to be R plus H. This is the situation. So therefore this is equal to root over of 23 into half into r by r plus h. That means the reciprocal of this, that is 2 by, if I am not wrong, half outside, r by r plus h means reciprocal 2 by 15 to the power 1 by 3, and therefore this is equal to root over of 23 by 15 to the power 1 by 3, and that makes it equal to 10 into 2.3 by 15 to the power 1 by 3, and there you get your answer as equal to n equal to 2.3. So therefore the answer of this question is going to be 2.3. This is a JEE 2022 advanced question. And you see, this particular question involves a lot of calculation and your understanding about interaction of masses, the changes in different aspects, masses and radius, handling them properly in a calculation. When they say density of the shell, you should not make the density of the entire volume. And like this, these things are calculated, long, patience requiring, and rigorous. That's where you can get a good benefit, a good result of advanced. Thank you for your patience, and see you in the next question.